Welcome back. In this lecture, we are going to talk about arbitrary mesh interface. This particular simulation of a overset mesh. There is a overset mesh over a background mesh, and this particular overset mesh is rotating. If I run this, you can see this is rotating. If I look at velocity, you can clearly see that it is rotating, which is causing this velocity field to have the highest value, and due to viscosity, it is showing some kind of gradient. We want to create a mesh interface which is of circular shape such that we can have a rotatory zone in the middle, and along the circular interface we want a mesh interface where we want to perform the interpolation that has better accuracy compared to an overset mesh. Wherever we can have a arbitrary mesh interface like a sliding mesh or a rotating mesh, we should prefer that over overset mesh. Let's get started. I have copied everything here. I'll first clean this home list, and so in the block.meshdict we already have the entire domain. We don't have to touch this. We should remove this because we don't want this inside geometry anymore. This is the bigger domain, and we'll use SnappyHexMesh to create the domain inside. For that, we will use Gmsh. It is easy to create geometries like a square and a rotating zone. Let me create one. I'll create it here. I think we already have one, which is this one. It is the entire thing. Let me remove all these. Remove square and spline object. And we also don't need this dynamic code. We have cleaned this particular folder. Now I'll create one file which is the square.geo. This one I'll open in Gmsh, square.geo, and I can create one point here, and then I'll get the script that I'll edit. I'll need the mesh point, mesh size equal to 0.1, and all these I have to populate. I want the center at 0, 0, 0. This I need from negative 0.05, negative 0.05, 0. Actually, we have the domain along the xz plane. So this is 0. Here we have the mesh size. And let me open this in Gmsh again. We have the 4 points. Let me connect them. And now we extrude along the y direction, negative 0.3 and 0. Now we can mesh this. This is not enough. So you can see everything is populated, and we'll change the mesh size to something finer. We want 0.01 or 0.005, and we have a fine mesh now. And we can save this as export as this, and we have to choose version 2. Remember this. We also need the STL file for this. So square.stl. We can also copy this and create the outer rotating zone. First, let me run block mesh. Block mesh is having some problem. 0 to 1. We don't have overset anymore, and this is also not required. Sides, these two not required, and everything else is same. Now let's open this STL file and see if it is at the right place. This is the block mesh without any hole, and let's open this, which is the STL file. This is not at the right location. We should choose the opposite direction, extrusion in the opposite direction. This should be 0.3. And let's again open Gmesh and remesh this and save. Export STL. And again, let's confirm. actually we should have this from negative 0.15. Then we'll have the extrusion in the opposite direction. Then it should work. Let's try this again. Finally, we have this dissecting this particular block mesh. Now, if we use the SnappyHexMesh, then it will create the mesh around this correctly. But before that, we need a rotating zone. We'll copy this square geo to rotating.geo. Then open this. Here I'll create one more point, which is point 0, which is 0, 0, 0, size, and all these I can remove, and this should be from negative 0.15 to positive 0.15, and mesh size also we should increase a little bit, make it 0.01. Now I'll again open Gmsh, the rotating.geo. You can see you have these 3 points only. I think some typo. Here we should have a semicolon. Now open this. We have these 4 points, but without this, that means we need this negative 0.15. All the points on the same plane. Now we can create arc, circular arc. First select the starting point, the center, and the end point. Similarly follow. Now we can extrude negative 0.0. We don't want extrusion to the mesh, and create this. I think I selected the wrong direction, but you can fix that in the script. But before that, we'll create surfaces along this. Remember, whenever you are creating a rotating zone, you should make sure that it is entirely closed. It cannot be open like we had the cylinder. This we have to close, and this one also we have to close. And let's also look at the normals. Let's first fix this in the script. This should be 0. We have this now, and let's create a 2D mesh of this and export as dating.htl in the ASCII format. We can check whether we have created this extrusion in the right direction from this. This should be 0.3 positive. Let's make this as positive as well. Again, go here and create the mesh and export. You can clearly see the rotating zone is going through the domain and the cylinder as well. Now we can go to SnappyHexMesh and use these two while creating the mesh. For that, we have to go here. This is an old SnappyHexMeshDict. We'll use the same one. First of all, we have to copy everything, all the STL files, to constant try surface. Make sure your try surface have all the files, so cylinder and this, and here we had the square and rotating. Let me change this in the SnappyHexMesh. This is the square, this is also the square, and then we can add another one, which is the rotating zone. We can name it as rotating, this also rotating. So except this, nothing much we need to change for now. Here also we should have a patch. Since our rotating zone is not a standard patch as a cylinder, so that's why it's not going to be a wall. This cylinder is a wall, but our rotating patch it's not a wall. For this we have to take care of that. Here, similar to this, we can have a level. It will have a minimum level 2. That means whatever is the level of the original mesh, it will just divide it by 2 to power 2. That means it's divided by 2 times, and that will be the minimum as well as the maximum mesh refinement. Then the face type is the boundary, and then we have to say what kind of phase zone this is. This is a rotating zone. This is a keyword. You cannot have any name here. And the cell zone is also rotating zone. and then the cell zone which is inside is the one which is going to rotate. Therefore, the rotating zone is the inside one. For this one as well, you can have a refinement level for the rotating zone as well. Since the name is rotating as well as here, you have to consistently use that one. There is a typo here. And then in the snap control, you can use the same values here as well. We are not adding any layers. Once this is done, you can directly run SnappyHexMesh and always overwrite. That means there is some problem with the normals. Let's check that. For a square, let's check the normals. Go to Tools, Options. Here, you'll see for the mesh, you can check the normals. Scale it by 100 and check. Let's scale it by 10, 30. All the normals are consistently pointing inside. That is okay. Let's look at the rotating zone. Here, we could have a problem. We make this 50. Check. All the normals are pointing inside, but this face is pointing out. So this is inconsistent. We'll open MeshLab to fix this. Just import the mesh. Here you can see one face has different color than others. You can go to filters, then normal curvature, and then reorient all faces coherently. And then they should usually face outward. You can just invert face orientation and then apply, and it will invert it. And then you can save, export. We can also do surface check on rotating. There is no problem, surface is closed, and now we can try running this. Let me also make sure that the cylinder is also pointing outwards. So we can go to this and the square cylinder. This is pointing inwards. I'll just make sure it is coherently pointing somewhere and then invert the face orientation, and now it is pointing outwards, and then save, export mesh. Now I can again copy it and then run SnappyHexMesh. Let me remove everything first, constant polymesh, and then run block mesh, and then SnappyHexMesh override. There is some problem. Let me try to fix that. The location in mesh we have not set correctly. This should be outside the rotating zone. Rotating zone, it has negative 0.15. I'll select something like this. Once I do this, then also the same problem. Let me again remove everything to block mesh and then try SnappyHexMesh. Let's do these one by one. Clearly there is some problem with the cylinder. So this is square, this is square, and this is cylinder. That's why there is a problem. And similarly here. Now it has created these. So without any rotating zone, it should clearly show the interface. Now let's turn on the snapping, because there was no snapping, that's why it did not happen. It's still not working. Here you can see that we have this empty type for the sides. Always make sure whenever you are using SnappyHexMesh, it should not have any wedge or empty kind of boundary condition. We'll replace this with patch, and then once our SnappyHexMesh is done, then we'll manually edit this. Now if I remove everything again and then run block mesh and then run SnappyHexMesh, then you can see it is working fine. Now if I open ParaView and activate surface with edges, you can see that there is an interface which has been created, and for this interface, if you go to boundary inside constant polymesh boundary, you'll see that these are already created, which are rotating a rotating slave. These are created because in the SnappyHexMesh, we assigned this as a rotating zone. Therefore, it created this surface as well as a slave surface for that. Now, we'll create PatchDict to create a cyclic AMI patch, which is Arbitrary Mesh Interface. And that will be useful because we'll be able to interpolate from the master face to the slave face. We'll first create this file, createPatchDict. And here, these are standard. Then you have to write patches. There should be a semicolon at the end. And then inside this, you can define various dictionaries, which will be those patches which you want to assign some different type. The first one is AMI1, let's say this one. And then we have to write the patch info. The type is cyclic AMI. And then the match tolerance will keep as 0.001. And then the transform will keep as no ordering, and then we have to tell that which is the neighboring patch. The neighbor patch is AMI2, which we will create after this one. And then we have to write that how we are constructing this. Construct from patches. These patches we have created, the patches are rotating, right? Now the next one, we'll copy this one and then write this as AMI2, which is again everything is same, and the neighboring patch for this one is AMI1, and we are creating this from patches, which is the slave. Now if I run create patch, and always remember that you have to overwrite the original mesh. There was some problem because we had a typo here. This we did not close. This ran, and here if you go back to the boundary, you'll see that this is now a cyclic AMI type and various other things which are assigned now. You can run this without any problem. I'll just rename this as .old, and we don't want to run any dynamic mesh for now. So this is also .old. Now for pressure, there is no overset mesh. So sides, again we can go here and change sides to empty, and then have this as empty, and then instead of hole we have a cylinder, and we have AMI1 and AMI2. For this we just have to write AMI1, which is cyclic AMI, and AMI2, which is also cyclic AMI type. Similarly for velocity, this is now square. Let me just confirm if this is a square. This is a cylinder. This is a cylinder, and then this keep 0, and overset mesh is not there. And then again AMI1, which is of type cyclic, and AMI2, which is of type cyclic again. And here the velocities will keep as 0 as for others. After this much, we don't need anything else, and we can try to run this. Let's make this also 0. So other things, for example, in controlDict, we are going to run PimpleFoam, and in FA scheme, the things which are not, the scheme is not using, won't be used. It won't affect the overall simulation. Now we'll run this PimpleFoam. Maybe we'll remove this line number 19. Here we forgot the semicolon. You have to put the semicolon and then run. Again, there is a typo, I guess. Entity type has 2 access streams, so somewhere we missed the semicolon. Here there is no problem. Here also no problem. Here we missed the semicolon. Here we have to fix the solvers as well, because these we were using with overset mesh. For pressure, we are using this one. We will use the following solvers and remove all this and again try to run. So now it's running. You can see that here the solver is PCG and the preconditioner is a multigrid preconditioner, and then for pressure we use a multigrid, and for P final as well, whatever we use for pressure, and for velocity we use a smooth solver, and everything else is straightforward. Now we can just check the solution, whatever that has been run so far. So you can see, even though we have a interface here, which you can see here, because we have used a AMI kind of interface boundary condition, therefore there is no difference in the solution. You can still get the solution correctly. Just run another time step and you can see that it is seamless. There is no indication that there is an interface here. Now what we'll do is we'll move this interface. In order to move this, we have to add two more files, which is the point displacement. I'll rename this as point displacement, takes care of the displacement of each and every point, and this one, which is the dynamic mesh. This will move the mesh. Here we do not have to use a dynamic overset mesh. We'll just use dynamic motion solver FV mesh, and then motion leaps are same as before. And here we can have a multi-solid motion solver, as well as we can have a solid body. It does not matter. And this will remain the same. Our rotating zone is centered around the origin. This will remain the same. Our axis is this, and our rotation speed will remain this. And let's look at the point displacement. In the point displacement, we do not have overset now, and this is cylinder. And for AMIs, we'll use same cyclic AMI, and AMI2 also we'll use cyclic. And now we'll rerun. We'll first clean everything and then rerun. So valid zone is rotating zone. I think we have this as moving zone. I have to change this to the name that we have set to the zone, rotating zone here, and then you can clearly see that it is running fine. Now the mesh will rotate with this omega, which is 10, and with this you have an inlet velocity as well. You will see some kind of velocity gradient around the interface of the AMI as well. Let me see how many points we have. We have one time step. We'll wait for some time. We have 3 time data, so we'll just look at them. Let's look at the mesh first. Clearly it has moved. Earlier it was aligned, and then the next time step you can see it is rotating. You can also see the body rotating. And now let's look at the pressure and velocity. This is how pressure behaved. Then this is velocity. So you can see that due to the rotation, there is some different kind of vortex shedding that you can observe. With this, we'll stop this particular lecture. In the next lecture, we'll talk about sliding AMIs. You can also have mesh to slide over each other, and you can have the mesh interpolation take place in between those interfaces. If you like the content of our channel, then please like, share, and subscribe. Thank you.